But I got the important part. The year is less important than the play.
Yeah, Kaden from Rice University. We've talked to us about Untitled SUN Hubbard system.
Cool. Yeah, thank you for sticking around here to the last day. I apologize. I'm sure that won't be the last typo in the slides, but hopefully the most severe. This talk, despite the apparent implication of the typo, is very, very new stuff. I need the microphone.
You read my mic.
Like, I think Christian was doing that with you yesterday, reading your mind. There we go. Can you hear me in the back? Okay. Good. So this is actually some really fresh material. A lot of the calculations have been done in the last few months. Multiple plots were sent to me last night, and at least 2 of the graphs I'll be showing were sent to me while Simon was talking this morning, so it's all very hot off the press. It's been motivated by wonderful experiments, largely some that we heard about from Simon this morning, others by Yoshiro Takahashi, Leonardo Filani, that have made amazing progress with these ultra-cold SUN models, and I'll try to sell why we like these models so much without overselling it, but I am very excited about these models. So because who knows how far I'll get into all the new stuff, before I start, I really wanted to put up sort of all the collaborators that were involved in the things I'm showing you today. It's not a small crew of people. There have been a lot of people that have been involved. I probably won't do a great job of acknowledging every specific one in every place, but they've all played a big role. I don't know, I'm kind of the figurehead. I just am here to speak on their behalf. But if you want to, learn more, Eduardo's here at the conference, Richard's here at the conference, Simon's here at the conference, Fabiano. So go talk to them. They can tell you more about lots of the things we've been doing. And Yoshiro was really a stand-in for his big group that I've briefly put up there. All right, so I'm going to start this talk in an awkward way for the last day of the conference. I'm going to ask, why do we want to simulate Fermi-Hubbard models? That is the name of the workshop. But understanding why we want to do this, I think, will help give us some perspective on why we want to study SUN systems. So, there's not one answer. You can all have other answers if we, just shout out some ideas if you have other answers than I do. But I think one of the reasons we like to think about this is we want to get insights into real solid-state materials. Things like high-temperature superconductors, heavy fermions, other mod-insulator metal transitions. Other reasons we might want to study this is we just like to see novel phases. We're physicists. We're intrigued by things that don't behave in expected ways. And so we like to go hunt for new phases of matter. Another thing is to, especially in light of some of the things that have been going on with digital quantum computation, we might want to somehow demonstrate that nature has powers beyond that of a classical computer, this idea of quantum advantage or supremacy. And so maybe we want to show something like that. And these are challenging things to do from our field. One of the beautiful things about the plain vanilla square lattice SU2 Hubbard model is that it is a simple model that has a lot of really rich physics we've heard about, but on the other hand, it is a very special model. It has a lot of fine-tuned physics that you don't expect in a generic model. So maybe the most prominent, and several people have touched on this, is that in plain vanilla Hubbard, you really have perfect Fermi surface nesting at the same place you have a mod insulator. So if you have one particle per site, you're going to have a perfectly nested Fermi surface. That is not the generic situation. Most real materials, just because you have an integer filling, you will have a mod insulator if you have strong interactions, but you're not going to have that perfect nesting. And so you have to be a little worried, is the physics that comes out of all of these quantum simulations with SU2 square lattice, is it because of features that can teach us about real materials, or is it really tainted by this? We're just seeing the nesting effects or something. And this one way to think about this is for SU2 square lattice Hubbard at one particle per site, it's always an insulator. There's no metal insulator transition. The perfect nesting at weak coupling drives an insulator. At strong coupling, it's also an insulator. No metal insulator transition. However, if you can break this, if you can disentangle these two effects, now you can look at metal insulator transitions, which are very common in real materials. So that's one issue with SU2 on square lattice. Of course, we've heard actually another way of of dealing with this, working more generally, is triangular lattice, honeycomb lattice. Those will break this perfect nesting and give you a way to explore that. There are other ways SU2 is very special that maybe aren't tied as much to the nesting, but I think that's the most important one. The temperatures are, quote, high. I mean, they're nanokelvin or whatever, but they're high compared to the ordering temperatures of the phases we want to study or other phenomena that we want to study. So we heard in Christian's talk, for example, that we can't, how can we get below temperature of 0.2 times the tunneling? That's a major obstacle that seems to confront lots of these platforms. And tied to that, lots of the novel behaviors we want to see are at way below that temperature. A lot of them are 0.1 T, 0.01 T. I think ZXGen, you say, 0.001 T when you think about it this way. It's really, we need to get a lot lower. So that's a challenge for us. And then finally, for demonstrating beyond classical sort of quantum complex behaviors, that's something that is very challenging for SU2 already. But there have been so many algorithmic developments that there is starting to be a little bit of convergence about a lot of properties of the SU2 Hubbard model. So what I want to claim is that actually SUN Hubbard models address all of these big challenges in serious ways. So on the first point, when we have n not equal to 2, if I have n equal 3, 4, 5, 6, we heard those were allowed. And I'm going to discuss more what an SUN Hubbard model is and all this stuff later. But just to motivate us, if n is not equal to 2, then these are the Fermi surfaces up on the screen here. I guess maybe I can point so people online see it. If anyone watches. Up there are the Fermi surfaces. So you can see that for n equal 2, you have the perfect nesting. But if I have one particle per site, I have to decrease the filling per particle as I increase n to maintain the same total density. And so the Fermi surfaces shrink as n gets larger. You lose the perfect nesting. This gives us a tuning knob to disentangle how much nesting we want to have at integer filling. Very similar to the T prime over T ratio in a triangular lattice. Okay.
Sorry.
Yep.
What exactly is the half-filling condition now when you have n equal to 3,
So,
for example?
okay, great. So let's think about this. The possible states you can have on one lattice site for SUN are just you can have you have 6 different flavors, let's say, for SU6. And so you could have one particle in any of 6 different flavors, or I could have 2 particles, and then I have 6 choose 2 ways of putting the flavors
Right,
on.
so that's why
So-
the half-filling condition has to be different.
This is, yeah, so I'm not talking about half filling here.
Okay.
So I'm talking about
You're talking about n equal to 1.
I'm talking about the density is equal to 1.
Okay.
The half filling case is very interesting in its own right, and then it would still be perfectly nested, which
Exactly.
is something you're seeing.
Yeah.
That's actually not so relevant for most cold atoms, because if you start putting on average, say you have SU6, if you on average have 3 particles per site, your lifetimes are probably not going to be great, especially because you're going to have fluctuations to 4 or 5 particles. You're going to have 3-body recombination that's pretty quick. So we like to work at densities that are somewhat lower, but
And my point is just that if you want to go, if you're going to be away from half-filling, you can do that with SU2 as well.
you can go away from half filling for SU2, but in SU2 when you go away from half filling, you're not at an integer filling and you don't get a mod insulator. For SU3 you can stay at an integer filling, still get a mod insulator, but you don't have nesting.
Okay.
So it's a way of, you might say mottness and nesting, or mott and slater, or however you want to think about this. It gives you a knob to tune which of these is more important. Yeah. And so,
Thank
so that's really my argument, that that's a neat tool to have, just like with the triangular lattices. Another reason was precisely how can we get below T equal 0.2 tunneling, and I restrained myself from saying yesterday that, well, in SUN, SU6, our collaborators have already achieved 0.1 times the tunneling. And now we can have an extended discussion, and maybe we'll have it later in the talk, hopefully not yet. Is temperature the right thing to compare? Am I comparing apples to apples, or am I cheating in this? I don't think I'm cheating. I think this is genuinely colder in an important way. But of course, it's not the same system. Nevertheless, due to the intrinsic physics of this SUN, you get colder, and that's been experimentally observed. And this has led to seeing magnetic correlations in that system. And finally, I will hope to convince you, it's a disappointing conclusion maybe, or it depends on your perspective, but we have tried now at least 5 distinct different sophisticated numerical algorithms, and every one of them is struggling tremendously with SUN, much more so than for the SU2 case. All right, so this is my take-home message. I'm going to try and convince you that I'm not lying or sweeping something under the rug for the rest of the talk, and show you the progress we have made with all of these algorithms and insights into understanding the SUN physics. All right, so here, not a panacea, but a cause for excitement. And then just because I think it's cool to put on this is this graph we've seen several times at this workshop that I think Fabian and Annabelle put together. This is all the temperatures of 2D systems. There's a 3D that I've cut off of here from Randy that's a bit warmer. I think it's about 1.5 for T over the super exchange temperature. T over the super exchange in these experiments I mentioned for SU6 is about 0.38. Okay, so it's actually also the lowest in terms of T over J, not just T over T. And I did that just before the talk, so you should check my math, but I think it's okay. All right. All right, so we all know that SU2 Hubbard, I'm going to call it red and blue instead of spin up and down and not say anything else about it. If we move to the alkaline earth atoms, we already heard this morning, they have this special interaction structure. There's no hyperfine coupling. For alkali atoms, there's a hyperfine coupling. Collisions depend on the electrons, and so the collisions depend on the nuclear, the full hyperfine state. For alkaline earth atoms, the electron spin decouples from the nuclear spin because it's in a singlet state. The electrons are in a singlet state, and so when they collide, the electrons don't care what the nuclear spin is doing, and that's why we get this special symmetry. And the special symmetry is nothing but what we already saw this morning, that we have atoms that can tunnel from site to site just like before, and every one of the species, there are N species now if you like, have the same tunneling rate. So just like up and down had the same tunneling rate, now we have red, green, blue, purple, yellow, magenta. Anyway, so we have all these different things with the same tunneling rate. And the interactions also have a special symmetry, that the interactions of every pair, regardless of what the colors of the pairs are identical. Okay, so to understand the physics, everything I'm going to be showing you, it has a lot of similarities with SU2. One thing that will be important for the patterns that we've seen and will see is that super exchange works just like it does for SU2. If two fermions are in the same state, they can't get past each other, and so that localizes the fermions, they pay a kinetic energy cost. If two fermions are in different states, like up and down, now they can pass through each other. Delocalizing particles in quantum mechanics lowers the energy. Same thing happens with SUN. Right? In the U greater than T limit, it's this 4T squared over U effect, but it's true for all values of U. Furthermore, you might think going to large N makes things classical. With the terbium, we can go to N equals 6. With strontium, we can go to N equal 10. That is, in fact, not true. The SUN symmetry preserves the quantum fluctuations even as N goes to infinity in this system. I'm happy to give you that argument, but I'm going to skip it if nobody asks. So you have 5 seconds to ask, or I'm going to keep going. I'm used to awkward silences.
Do it.
Oh, okay. But I deleted the slide, but I can do it with my hands. So, for SU2, for spin 1/2 SU2, or in fact larger spin SU2, you get something like an S.S Hamiltonian. What does Wigner-Eckert teach us? It teaches us that an S operator can raise or lower angular momentum by 1. So if I think about I have all these different angular momentum states on this atom, all these different ones on this atom, when they interact, I can go plus or minus 1 in one interaction event through super exchange, right? Just like a Heisenberg Hamiltonian. That means that my fluctuations are kind of order 1, even though my spin is order n big. And that's why quantum fluctuations get small for a large spin, for an SU2 large spin. But for SUN, you can see, going back to our picture here, that if I have a red on the left and a blue on the right, when they do this super exchange, it doesn't matter what my internal angular momentum is. So even if I'm at plus 5 angular momentum and minus 5 angular momentum, they can just swap. I can go plus 5, minus 5 to minus 5, 5. So the fluctuations are as big as I want. And so that's really why SUN guarantees the importance of these quantum fluctuations, or at least allows the importance of these quantum fluctuations. And that's substantiated by lots of large N calculations. Antoine.
Kaden, just a remark on this. So the way I would put it is that if we fix the size of the limitation, which is what you do when you went from a side and you present, it becomes very, very quantum.
Totally.
Right? But the largest semi-classical limit is we fix the group and we take the size of the limitation being large. There's also a semi-classical limit for SUN.
Yep.
Except it's not this one.
Yeah, it's really the same statement, except there are other ways of fixing the representation, like doing fundamental, anti-fundamental, fundamental, anti-fundamental.
We take fat representations, you know, with
Yep.
very bosonic,
Yep.
there would be a semi-class.
Totally, yep. But as long as you take, but in the limit that we care about, where we fix, say, one particle per site and take n large, that's when, you know, these quantum fluctuations stay large here that they wouldn't for SU2 in the usual situation. Okay, so what's the Hubbard phase diagram? Real quickly, since we already saw it, we go from up, down, blue, yellow, to this stripe order. This stripe order is going to make appearances later. So notice there are diagonal stripes from lower left to upper right at 45 degrees, all yellow, all blue, all red, and it just repeats. So that's interesting, you know, not that much more complicated than SU2, but interesting. SU4, I think we saw some hints of earlier as well. So this does two things. It breaks the translation symmetry and it breaks the spin symmetry. It does it in a really intriguing way. It makes SU2 singlets, so red-green minus green-blue on this bond, and then it makes a different type of singlet on the next bond, and then it tiles everything everywhere, okay? And so this is a very different symmetry breaking than a simple, say, diagonal stripe order. So why is that, and do we understand that? And then we get to SU5, good luck finding the pattern in this. This is, in fact, periodic. And if you push this further, there are these large N approaches that say you can get spin liquids for this model if you take an appropriate large N limit. Now, I would say that as you move to the right in this diagram, the complications of the calculations get more and more severe. And as you probably have interacted with a lot of theorists, or you are one yourself, you know that wishful thinking can set in as the calculations get harder and harder. I don't think that's the case for these spin liquids, but anyways, I would say that for SU5 and above, it's still very much a question what the ground state's truly going to be. So there's a lot of opportunity to start investigating this. Also, this is all just for the Heisenberg limit. So this is large U over T, one particle per site. We don't know what happens if you decrease U over T. So I go and add some itineracy. We don't know what happens if you dope the systems. These have just not been studied in any substantial way. Very, very simple calculations, but not in any serious way. Okay. So what I want to show you is that we are starting to make progress on this experimentally, our friends are, and theoretically. So this is a graph from, okay, so you can't complain about me not citing your paper because I don't cite my own papers here apparently. Anyways, this is a paper that was recently published in collaboration with Yoshiro Takahashi's group. There's a lot here, so let me sort of go step by step to tell you what's going on. They're plotting this quantity that they call the singlet triplet imbalance. I think we've heard this mentioned early in the conference. It's a measure of the spin-spin correlations, defined here on the right. This is just a measure of the propensity of if I have a certain color on one site to be in a different color on adjacent sites. So this is the ordering type of order that you'd expect in all the pictures I showed you before, and it's driven by the super exchange for reasons I explained. It's also defined in a way such that if you just had uncorrelated states, this goes to 0. So we're not sort of unfairly boosting things within either, and I can try and convince you of that. So the usual SU2 measurements, which they can control the N in their experiments from N2, 3, 4, 5, 6. This is N as a function of the entropy per particle. I or CNN is a function of the entropy per particle. And you see that as the entropy gets lower, the correlations increase. But the more important thing is compare this blue curve, which is the 1D SU2 case, to the green curve, which is the 1D SU6 case. Going from SU2 to SU6 is enormously increasing the size of your correlations. These are nearest neighbor correlations. And it's also boosting the entropy at which correlations set in. Okay, and this is what's really nice. You can actually prepare as low of an entropy gas with SUN as you can for SU2. And so you are able to see sort of deeper into the correlated physics region. Let me explain why that happens to you, and then we can talk about some more features on this graph. So the reason is very simple. The point is that the entropy you can accommodate in the spin alone. Imagine you're in the Mott limit, so there are no charge fluctuations. The entropy I can accommodate in spin is just log n. There are in different spin states, entropy is log n per site. And this tells me that if I decrease the entropy below log n, I have to have magnetic correlations. That's the only way I can decrease the entropy. And so as a cartoon, maybe I could have this green curve for SU6 zero down to here, but then once I get to log 6, it has to go up. For log 2, you can get a lot lower before this sets in. Right? And so that's really very suggestive, and you can compute this and the leading corrections to this in a sort of high temperature series expansion, and it confirms this picture. And that's really agreeing roughly with what we see here. Qualitatively, it's agreeing with this. You shouldn't take the numbers on the x-axis too seriously. This is averaged over a harmonically trapped gas, so there are regions of all kinds of densities. Together here, it's mostly 1 particle per site, but by no means all 1 particle per site. This is great. We were also able to do some theory, especially in the 1D cases. These solid lines are theory, coming just from exact diagonalization, using symmetries and some basis truncation that we're able to systematically converge. We get pretty good agreement with the experiment, not perfect, but I would say we're quite happy. And there's 0 fitting here. We're not fitting temperature, we're not fitting, nothing. So this was just, they handed us trap parameters, handed us their U over T, and this is what we got. I was very nervous before we made that plot, but it worked, yeah.
How large are the systems?
100,000 particles, 200,000 particles, maybe. Is that right, Eduardo?
Or you meant the
Both,
theory
actually,
one?
yeah, like, I mean, they...
Oh, in 1D, yeah.
Yeah, it's up
It's
to
still
8 sites.
200,000. Oh, the ED.
8 sites.
So you compare like 8 sites
So
to
we
like,
did 5 up to 8 sites, and then
Yeah. So apparently I didn't include
I
the
think
plot
that's
with
what
error
it-
bars. Maybe that's in a couple slides here.
I think it's in the previous slide.
Oh, okay. Okay. Sorry, there.
Yes.
This one has error bars. These error bars include the error from finite size extrapolation as well as, actually for that's all it's got, yeah.
How is the you measure it?
You know the initial entropy before you load it into the lattice, so they're assuming that it's unchanged, that it's adiabatic. They've done some checks, but I wouldn't say they've done extremely thorough checks, and that is a weakness that we absolutely, would love to understand better. Exactly, can we quantitatively understand, convince ourselves that it's equilibrated at the entropy claimed? Okay. How much time do I have? 10 minutes before questions or total? Oh, great. Oh, cool. That's cool. Okay. Well, then I'll slow down. All right. Right. The other thing I wanted to discuss about this was the 3D case. And actually, maybe since it's nicer on the first graph, let me go back here. So the 3D case, the experimental measurements are here between the two 1D curves. This is 3D SU6. We don't really have great calculation. We have this red curve here, which comes from determinantal quantum Monte Carlo. And getting that red curve was truly heroic efforts by Eduardo. But you can see the entropies we're able to converge down to are way, way higher than where they're getting experimentally. So in 3D, we have no chance of making predictions about their data with our DQMC method here. And I will suggest by lots of things later that none of the methods we've employed give us a chance of calculating any of this. So in terms of that first challenge, can we do quantum simulation that's well beyond the reach of our computational tools? I can firmly say yes with our existing computational tools. Now, I hope that I can change that and, then we'll turn that situation around. But I think it's going to require real insights into the physics and not just, optimizing things. Okay. That's fine. So it's colder. Is that enough? All right, so just because it's colder, do you actually get big, longer range correlations, or is this maybe just some nearest neighbor type correlation? Here I'm showing you plots from the 1D case where we actually can make the plots that indicate there are substantial longer range correlations, despite the fact this is a 1D system and you have these rapidly dropping power law correlations. So the nearest neighbor is this black curve. This is again the nearest neighbor, sorry, it's not A, it's the nearest neighbor correlator as a function of entropy per particle. And you see it gets up to about 0.5 at these low entropies. These are actually higher than the experimental entropies just because I didn't plot lower. The next nearest neighbor is about 0.15. The next nearest neighbor is about 0.05. So the next nearest neighbor is about 10% of the nearest neighbor correlator here, and the nearest neighbor correlators are extremely strong here. So you have substantial long-range correlations is what the theory predicts. Our collaborators are building a quantum gas microscope for ytterbium that will hopefully be able to image this directly. And in the higher dimensions, I would expect, this is substantially enhanced. In 1D, even at 0 temperature, correlations decay pretty quickly. So anyways, that's to be done. What we've done is we've tried to understand the 3D or 2D, actually the 2D correlations. This is wrong button. No, somebody slides. Okay. So this is a structure factor. I'm not going to talk about the structure factor. Instead, I'm going to show you a ton of graphs here in real space You don't have to pay that much attention to too many of them. This is some of the data that I just got, but I wanted to show you. So this is, the labels here are the interaction strength and the temperature. So hot is over on the right, cold is over on the left. Top to bottom, that's right. Top is the weak interaction, bottom is strong interactions. And the main thing I want to point out is that this red dot, that's the nearest neighbor interaction, and then the nearest neighbor correlation, the on-site correlation. Then the blocks just above and to its right, those are the nearest neighbor correlation. You can see those set on as you cool the temperature a little bit. And then so on, it goes out to longer range. But I want you to notice that the nearest neighbor correlations are anti-aligned. I want to be in a different color, like we expected. And that's true pretty much everywhere, at least everywhere that it's not statistical noise. I would ignore some of the lower temperature stuff. But something really interesting happens when I start looking at these graphs, and I'm not sure it comes out well on the projector, but I think you can see it okay. So look at this column where sort of in the middle, temperature of about 0.5 times the tunnel. The next nearest neighbor correlator goes from being negative at large U to being positive at small u it's negative, at large U it's positive. And so this goes from having sort of red, green, blue to red, green, and then a little bit of propensity to be back in the red state again. And this is something that's actually been predicted as a low temperature ordered state, but we've never had a clue what temperature you might see it at. And now we know the temperature is about 0.5. And remember, the experiments are at a temperature of 0.1. So they should be able to very strongly see things like this transition as a function of U, weak U at the top, strong U, going from positive to negative next nearest neighbor correlations. So I think that's really interesting and does suggest we are getting to interesting beyond nearest neighbor physics in the experiments if only they can measure it. Okay, equation of state, we've done a lot of work here. I'm not going to talk about since Simon talked about some of it. I did just want to say this was the graph that I got about an hour ago or 2 hours ago. So Peter told us that if I took the compressibility and I plotted as a function of temperature, and then I fit this to a e to the minus delta over t, like you'd expect for a gapped system, then this lets me extract the gap, and if I plot that versus u, I can diagnose phase transitions, metal insulator phase transitions. So I wouldn't take this too seriously yet. This is just very preliminary and have to think about things, but you can see that this is delta, the gap, is a function of u, and it looks like it's extrapolating to 0, or at least very rapidly approaching 0, somewhere in this kind of 5 to 8, u equal 5 to 8 window. And so this is exactly, if you remember early on I said because we don't have nesting, we expect a phase transition at finite u. This is a signature perhaps of that phase transition, and I will show you much better calculations that show you directly in the magnetic order that there's a phase transition there. But I do want to point out that how are they getting this? This is from analysis of data already between, this is a log scale, between about 0.3 T and 1 T. Again, this is warmer than the experiment, so experiments can do this analysis right away. Okay, all right. I'll pause for a second here. Anything we want to talk about? We've had a lot of questions already, but yeah.
So, in fact, this maximum compressibility already at high temperature has been discussed a lot in connections to MIT. This is the sort of window line.
Yeah, totally, yeah. Yeah, I mean, this is not a novel way of analyzing. This is a very conventional thing, yeah.
Just to make sure I understand, so presumably, like small u over t, the ground state is not. There could be other kinds of gaps that open up, right?
There could be, yeah. So we know that it should be a metal for small u. At least that would be the expectation. It's this stripy thing for large u. There could be intermediate phases that could be antiferromagnetic metals, or they could be some other sort of gap state. We don't know. In fact, we have some hints that there maybe is an intermediate phase, but I'm not going to talk about that. Yeah, that's a good point. Yeah.
Do you have that curve for various n in SU?
I asked for that, but he couldn't finish it over lunch. So this is just for n equals 3 or n equal, which n is this, Eduardo? It got cut off.
That's for n equal 3.
This is n equal 3. But this was exactly, so it would be nice to see for n equal 2 that it kind of goes like this. Actually, for n equal 2, there's an essential singularity, so I think it's kind of going to be a concave thing. But I think the trend with n will be very interesting to see if it does look like it's getting bigger. Okay, so that was just saying that's hard. what I want to advocate is that we've heard from Antoine and others about this. Oh yeah.
Can we go to the previous? But so y gap is equal to 0, like just means that it would not fit the power law, or
It means
because of exponential?
yeah, it means that it's clearly not even decreasing, right? So this is, for example, one of the cases where it's giving 0 gap, and it's just not even decreasing there. Where's the other one? So here, this actually does fit to a gap, but notice this is the log scale. So the gap scale is right around there, where it sort of bends down by about half. And you see that's like 10 to the minus 2, or a few times 10 to the...
0 on the scale.
It's really 10 to the minus 2, yeah. But I think it's really just not going to 0. That's right, yeah. Okay. So I would like to advocate, like we've so wonderfully had for the SU2 case, we've had these many methods start converging, and we start seeing tables where really people have tackled this problem with 20 methods and see they kind of agree, that we now have a chance to do the same thing with SUN with some of the motivation that I gave at the start of the talk to get these more transferable lessons. But now we have something new. So what I'm going to show you is we've done DQMC. We've also done an LCE. Simon showed that this morning. I won't revisit it. We've, our collaborator Ettore Vitali and Richard Scalatar and others have worked with us. They've came up with this constrained path quantum Monte Carlo algorithm, which is employed incredibly successfully, incredibly accurately for the SU2 case. And I'll show you briefly some calculations on that. We've done something called the two-particle self-consistent method. This is a simple field theory type method that, again, at high temperatures is very accurate for SU2. And a friend of ours, Evgeny Kozik, has done privately some diagrammatic QMC that I won't show. But importantly, we have a new messenger of experiment that really outpaces things. So I think we have the opportunity to redo this table, but now with experiment providing numbers for us to compare to in regimes that may not be easy to trust any of the theory. Okay, so I'm in the question period, a couple minutes into the question period. Okay, 5 minutes. Good, so let me pick and choose. So this is a phase diagram from the DMFT. The DMFT this is single site DMFT, but real space DMFT, so you can have symmetry breaking. I wouldn't call this an accurate theory. It's a sophisticated theory, but I wouldn't just trust it. But what you see is that indeed there's a metal down here at small interactions. At strong interactions at 0 temperature, there's this stripe order. They go 3 sublattice antiferromagnet, and if you heat it, you get this 2 sublattice order. And this 2 sublattice order, this positive, negative, that's exactly the type of order I was showing you was starting to appear in our DQMC calculations. So we think that we're really starting to see, maybe not the phase, but starting to see that type of order emerge. Remember, as we were at weak U, we weren't seeing that, and then we went to strong U and we started seeing that physics. This calculation is 3D. I'm just putting it up for motivation. They also did it in 2D. They just didn't show a graph. But they say it's the same thing, just with U shifted down in 2D, which I think is not super surprising for a DMFT calculation. Also notice the temperatures are about 0.3 times the tunneling. Again, DMFT may overestimate that, but their experiments are down here at 0.1 times the tunneling. So if that's right, we should be able to see all of this in the existing experiments.
Sorry, what's the SU2 line?
SU2.
Do you have TC for SU2 as the dashed gray line?
Yes, that's right.
3D or 2D?
It must be. I mean, it must be 3D or
Yeah.
0, right? I didn't actually pay attention to the dash line, but I assume it's the SU2 3D. But all of this is 3D here. What I'm going to show you next is 2D, where we did the calculations. I'll just advertise. These are the constrained path quantum Monte Carlo calculations. Structure factor is a function of U. The black line is the converged. We iterate this to self-consistency, and you see 0 structure factor at kink, and it goes up. And the last calculation I'll show you is this TPSC. TPSC is you just do RPA, random phase approximation. This is something that Henning Schlummer in the audience has done, a student of Fabian and Annabelle. RPA we all learned in kindergarten. So he did this calculation, it works terribly. RPA, of course, has a divergence when U is equal to inverse chi naught times 2. And so it doesn't capture the low temperature physics at all. These green curves don't agree with the red curves because of this divergence. RPA also fails to satisfy Pauli exclusion. Merman-Wagner is not satisfied. The TPSC corrects all of these by a careful vertex renormalization. And for SU2, this works amazingly. You see how well the blue curve reproduces the red curve in the temperature regime we're plotting here. For SUN, it's not so nice. For larger N, the TPSC is still capturing amazingly better than the RPA, but certainly not as nice as it was for SU2. So this is what many of us call the conservation of misery. The QMC struggles because it has a sign problem even at integer density. The NLC struggles because the Hilbert space is huge. The diagrammatic methods like TPSC struggle for who knows why, and we've heard the same thing about the diagrammatic Monte Carlo, that it is actually converging slower as n increases. So I'll leave you with that, and you can read the conclusions. In the interest of time, let me stop here. Thanks, y'all.
All right, we have time for a couple of questions.
Maybe I missed it, but is there a controlled large N calculation that one can do in this context?
That's a great question. So there is, as Antoine pointed out, if I fix the representation as n gets very large, there is a controlled large N calculation you can do. This has been done, and in fact, for representations so that it takes at least 5 or more particles to make a singlet, so the 5th representation, I guess, you get a chiral spinlet. And this is one of the things that really motivated a lot of people to look at this physics. But this goes, for other cases, looking, for example, where you take the fundamental representation, then the anti-fundamental, then the fundamental, then the anti-fundamental. I think that calculation was done by Subir in the 80s or something, and you'll get some valence bond crystal in that limit. Absolutely, there are controlled N limits. They're just not the large N limit that, it would be natural in these systems.
Kaden, you get the control large and the size of the position, the scale of N.
That's right. The ratio of N to the representation is like 5 in those cases, N over size of the representation.
So there is no control large N
For fixed representation. Yeah. And that's the case that's kind of interesting here. We always want to work around the fundamental or maybe the second representation.
There's no other question. Thank you again.